Okay, let's return back to the text here. You'll notice in the text that they refer to a lot of the things I have, the terminology of the base, for example, the input, the independent variable, x, right? That's the exponent in this case. Notice I used a -4 also as an example, and notice that they and I both put parentheses around it. We need to be careful with that. Okay, before moving on, let me show you what I mean by that. Okay. If I have -4, let's say, squared, that would be the negative of 4 squared, because the order of operations say exponentiation comes before things like signs. The reason why is because the sign is essentially the result of multiplying by -1. So this would be the negative of 4 squared. So that's -16. Whereas -4 squared, with the -4 in parentheses, will be the product of -4 times -4. In other words, the quantity of -4 altogether squared, and that's a positive 16. And since our function, in this case we would be saying something like f of x equals a to the x, where a is -4, we want the entirety of a raised to that exponent. And so that means you need to put parentheses around that 4. Okay, back to this. So, in your textbook, the OpenStax book, they look at a few examples of where a equals 2 and a equals 3, and then they want you to try a equals 4 and a equals 5. So because they've shown all those, we're going to use a different one. Okay. So first what I'm going to do here is I'm going to change to graph paper. Okay. Next thing, let's put an axes in here. Okay, there we go. And then next up, let's write a function. So what I'm going to do is I'm going to look at what if a equals 6. Okay, I'm picking this because it's a number greater than 1, but it's not one of the ones that they've already talked about or want you to try on your own. So we're going to use that. So that means our function is going to be f of x equals 6 to the x. So I'm going to wait to put any sort of scale on this before I know what kind of numbers I'm dealing with. So what I'm going to do is I'm going to start by making a table of values just so I can get a feel for things. Okay, it's always a good idea to pick a variety of values. Okay, for right now, let's just use let's use integers, and we'll use positives, negatives. And then if we want to, we can go and look at some fractions. So let's do -2, -1, 0, 1, and 2, and see what happens. I'm going to start with this biggest one down here, this 2, mainly because it's probably the one people are most used to, squaring things. That's probably the first exponent you learn about. Okay. Next up, going up from here, 6 to the first power. Well, anything to the first power is itself. Okay, 6 to the 0 power. Well, anything non-zero to the 0 power is 1. If you need to review that, that is covered in the OpenStax book when exponent properties are discussed. Okay, 6 to the -1/2. Well, raising something to negative power means it goes into the denominator. So we have 1 over 6 to the first power, in other words, 1/6. And finally, 6 to the -2 equals 1 over 6 squared. So that's 1 over 36. Okay, so if we wanted to fit all these on here, these here, the 1/36th and the 1/6, those are very, very small. Okay, so I don't want to, if I want to plot those, I would want to zoom in. But if I look over here at this bottom one, we go up to 36, that's pretty big. And so we'd want a much bigger scale. The issue is exponential functions grow really fast. And so generally, no single window that you look at on here is going to give you a good overall picture. You're either going to be zoomed in and be able to see the smaller values much better, or you're going to be zoomed out and see the bigger values better, or you're going to be zoomed somewhere in the middle and you'll just see the stuff close to the origin nicely. Okay, close to the origin in this case. If the function was different and transformed and whatnot, then it might not be near the origin. So what we're going to do is we're just going to try and fit this last point on here, the 2 and the 36. Right? Let's look at the points here. So if we try to fit this first point in here, that has an x-coordinate of -2 and a y-coordinate very close to 0. The next one, the y-coordinate isn't quite as close to 0. We're getting farther away from 0 on the y-axis, getting farther away, and then finally we are 36 units away from 0 on the y-axis. Okay, now that's just finally because I stopped at 2, right? Now it's not finally in general. The domain of f, let's go ahead and write that down, is all real numbers. Okay, and there are no gaps in there. That's one of the things we made happen by choosing a non-negative, non-zero a. Okay, so if we want to fit that on here, then that means we want to somehow fit 36 on here. So let's see how much room I have to work with. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so because there's 18 here, looks like I could probably fit that on by skipping by 2's. So that means, let's go back to here. So this would be a 2, 4, 6. Let's go ahead and mark 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, and then obviously it can keep going. I shouldn't say obviously, it's only obvious because we already talked about that. Okay, let's go to the left. Now keep in mind what I'm doing here is the x-axis. The outputs we've been talking about are on the y-axis. So I could, if I wanted to, use a completely different scale for the x-axis and y-axis. And I don't need to fit all these in on the x-axis. The reason I'm showing, I'm using the same scale on the, on both axes. I really shouldn't try and talk and write at the same time. The reason though is just because when you have the same scale, it doesn't get skewed in various ways. When you have different scales, it can make it look differently than you're expecting it to. Okay, so let's go over here. Okay, still just using the same scale. That's not 118, that's 18. There we go. Again, it keeps going. Okay, we'll see that the range is not all real numbers. It does go up forever, but we'll see it actually has a limit when going down the axis. And you might have predicted that we don't actually need to show all this down here. because notice all of these are positive, but you might be thinking, well, maybe we just didn't go far enough. So think about that while we're doing this, and then later we will check to see if that prediction is correct. So again, I'm going to start with this this last point over here. So 2, 36. So remember, we skip counted by 2's on this axis. So 2 is just 1 unit to the right, not 1 unit, 2 units, 1 mark to the right of the origin. And then 36 is all the way up here. Okay. Next up, we have 1, 6. So 1 is halfway between the origin and that first mark. And then 6 is up those 3 marks there. And then 0, 1, so that's right here. And then we have -1, 1/6. That means -1 is halfway between the origin and the first mark on the left. And 1/6 is just 1/6 of the way between the origin and the height that we marked this previous dot at. So this is already getting very close to the x-axis according to our picture. Okay. In fact, because of the fact that my pen is not an actual point, right? We make something that you can see. It's gonna overlap with the axis, even though the point it represents does not. It's still above the axis. It's just very tiny. And then finally, -2, 1/36. So that means we're now 6 times smaller than the previous point. The only way to draw this is to pretty much draw it on the x-axis. Okay, it looks like it's about the same height. And let's see if that makes sense. Okay, we're raising 6 to these powers that are getting smaller and smaller by way of getting being negative numbers farther and farther away from 0, which means we have 1/6 raised to larger and larger numbers. Well, if you raise 6 to a large number, you're going to get a large number. And then if you divide that into 1, right, if you have 1 pizza and you're dividing that among 36 people, you're going to get a tiny bit of pizza. So if you're raising 6 to even bigger powers and dividing 1 by those bigger powers, dividing 1 by 6 raised to those bigger powers, you're going to get something smaller and smaller and smaller. It's never going to be negative. Right? If you have pizza, it doesn't matter how many people you're sharing with, you're never going to get negative pizza, right? You're not going to have to somehow produce pizza, okay? It just means you're going to get less and less and less of it, or, what is going to feel like essentially nothing, because there's limits to how small we can slice pizza. But in math, there's no limit to how small you can slice the number 1. So what this means is the numbers will be getting closer and closer and closer to this x-axis here. And so, as we move to the left, or in this case, just because it's easier, oh shoot. As we move here, I'm moving from the left to the right, just because it's easier for me to draw it without making so many mistakes. Okay, but as we would move to the left along here, we're actually getting closer and closer to the x-axis. I cannot draw perfectly. I will show you a better graph in a moment where it is done pretty much perfectly, but this is about as good as I can get by hand. Now let's look at what happens as we move to the right. Well, it appears to be going upward quite fast. And if you're concerned, thinking, well, there might be something in between here, maybe it goes up and down, something like that, we can try in between values. Okay, so for example, what if I tried something between 0 and 1, like say 1/2? So it'd be 6 to the 1/2. In other words, radical 6. This is an irrational number. So I am going to grab my calculator for this one. And if I take the radical of 6, I get 2.449489743 and so on. So this is about 6, oh, sorry, not 6. This is about 2.45. So our point is going to be 1/2, comma 2.45 approximately. Okay, this one is an approximation. Okay, so let's see where that is on here. Okay, 1/2 would be halfway between these 2 points, the one on the y-axis and the one that I'm hovering over right here. And then the height will be 2.45. So 2.45 is about right here. Okay, and you can see that if we draw this line, this curve, I should say, in here, that's about where we expect it to be. It turns out that the graph of y equals f of x is what we call smooth. Now, there's actually a meaning of smooth in mathematics. We won't be going over that. That's a calculus topic. But luckily, it transfers over to the way we use smooth in everyday life. It's going to look nice and smooth. Okay, not any jagged edges. Okay. Again, this isn't a great picture, right? I'm using just a pen here, and that's going to be a little wobbly. So let's go ahead and look at what it should appear to be. Okay, so I'm going to go over to Desmos. Okay, and I'm going to type in f of x equals 6 to the x power. And so here you can see at this point where I have my cursor at -2, this one was at 1/36. Okay, so you can see that point here. In fact, let's go ahead and plot that. Okay, -2, 1/36. Okay, and you can see that point lies exactly on that curve where we expect it to be. But this one is drawn a lot nicer. Okay, so 1/36 is approximately 0.028. So if we put the label on here, you can see approximately where that is. Okay, let's do another one. Let's look at the fact that we know that -1, 1/6 is on here. Okay, and sure enough, it is on the curve, and that's where we expect it to be, right? A little bit higher than that. We see 0, 1 is right here. If we plug in 1, which is right here, we get 6, and that's that point right there. Okay. If I want to see the other one, I'm either going to have to keep dragging this, or I can zoom out. I'm doing that with my scroll wheel. Okay. And now I'm high enough that I'll be able to see it if I put it in here. So let's go ahead and put in 2,36. Okay, and there's our point right there. Okay, so that is showcasing 3 particular points, but we could do this with all sorts of other points. So let's say you wanted to look at the one we added afterward, the 1/2, 6 to the 1/2, okay, which was the square root, or technically it's the non-negative square root of 6, but people often just say square root, but we should say radical. So radical 6, and sure enough, there it is right here. Okay, so this gives you a better idea, and you can see how if I zoom out, I can see how fast it grows, but that makes it really hard to see what's going on up close. If I zoom in, I can see what's going around near here, or if I want to see what's going around on the small side, I have to zoom in a lot more. Okay, and so you can see as I zoom in, you can see, oh, yep, it's not, it looks like maybe it's touching here, but if we zoom in, nope, not touching there, maybe it's touching over here. Okay, so we zoom in over here, nope, not touching, and you can do this forever and you'll see it never actually touches the x-axis. Okay, so that's the graph when the base is greater than 1.